Here's a brief introduction to the wave equation. The situation here is that we've got a function u of xt, as we did in the heat equation, but now it means something different. We want to picture a string, a stretched string under some tension, stretched along the x direction, and then I can move it, I can pluck it or stretch it transversely to that into the y direction. And u of xt is going to be the displacement at a particular place x and a particular time t. So once again, we could graph the whole three-dimensional graph, the surface in 2 dimensions, with x and t both being on the same footing. But we don't need to, especially since it makes sense to think of t equals t snapshots at particular fixed times t. So suppose, for example, that we started out with the string stretched upward in this first part and downward here. What should happen? Well, the tension in the string is going to create a restoring force that's going to want to pull those back to center. And so later on, I'll draw it a little bit smaller here. Later on, it's going to be a smaller amplitude here and a smaller amplitude here. We don't know if there might be some magic shape that sort of stays the same shape, although you can probably guess what it might be if the world is nice to us, and it is. And we can't be 100% sure if this stays exactly 0, although we might guess if these are exactly symmetrical to each other, we might guess that that stays 0. But let's draw it as if it does. Now, we're still going to get some motion downward. And here's something that's very different from the wave equation. There's going to be a moment when it's exactly 0, or very different from the heat equation, rather. There's going to be a moment when it might be exactly 0. Again, depends on exactly the shapes and whether it's symmetrical or not. But say maybe this is t equals 1, maybe this is t equals 2. And then after that, I'm going to try and fit it in here, even though actually, I can combine some pieces of paper, maybe. Yeah. Let's do this. After that, we're going to have, what's going to happen? These guys still moving. There's still a red arrow here. And this part of the string is moving down, this part is moving up. And so it's going to rebound, it's going to come up in the opposite direction. Like this, maybe at t equals 3. And then maybe come all the way to still moving. But now it's going to be slowing down. Because as it goes, that force is now not wanting it to stretch in that direction. And so eventually it's going to stop, maybe at t equals 4 or something. It's going to stop, and then it's going to turn around and bounce back and forth. So that's what we would expect, is it'd start in this configuration up here, and then maybe go through something close to 0, and then get to the other extreme, and then oscillate back and forth. Okay, so that's the kind of thing we'd like to predict. And let's go back to that very first one and think about what's happening here. It's about forces. The story here is not about a dissipation of heat or something like that. It's about forces making things move. And so if I analyze the little section of the string here, it's going to be pulled downward with a force. F is going to be negative. That does not mean the velocity is immediately negative. If I start this from rest, this red arrow might be a little misleading here, because if I start this from rest, it's not going to immediately start moving, but it's going to start accelerating. And what is that acceleration? It's the rate of change. It's the second derivative of u with respect to t, because u measures how high it is on this graph, and acceleration is always the second derivative with respect to time. And so here's a point where utt is supposed to be less than 0. Now, does that correspond to anything we can measure in the x derivatives? Well, this is a point. What's special about this point is that it's curving downward. And because it's curving downward, it's got a piece of string that's pulling it, let me use blue arrows here, that's pulling it down and left and down and right, and the upshot of it was that it went down. That's not going to happen unless this thing is concave down. In other words, uxx is less than 0. So here's the analog to what we had in the heat equation. There's a link between t derivatives and x derivatives. But here, the proportionality is between uxx and utt, not between uxx and ut. And that's a big difference, although there's definitely a lot of the theory that works, the setup for the theory tends to work in the same in the two cases. But this is a very big difference. Similarly here, over here, this is a place where it's concave up. And what's going to happen, it's going to be accelerated upward because the string is pulling it upward. And so UTT is going to be 0, greater than 0. But speaking of equaling 0, let's check that in another case. We should be able to analyze the steady state case. Well, if I just held the string here, and then I held the string over here at some fixed displacement, and I have a straight line where uxx is equal to 0 for all x, then I'm predicting that UTT should be equal to 0. Well, let's see. Should it be accelerating one way or another? Well, if I just stretch it out, and I hold it at this point and this point, should it just start moving? Should it start accelerating in and of itself? Should it start bending and vibrating? I don't think so. I think that's correct. So that is another check that this makes some sense. Okay. So once again, the big leap is not that these things are connected. It's hopefully this convinces you that it has to be something about the relationship between these two. I guess there's two big leaps. One is that nothing else fundamentally comes in, like first derivatives. And for more elaborate versions of this story, maybe first derivatives or even third derivatives or something might come in. And that's certainly a big assumption, is it's not that complicated. And then the other big leap is that they are not just related, that just like in the heat equation, they're proportional. And it turns out that they are proportional in a lot of situations, and the wave equation is exactly this. And here, I wasn't making a big deal about what the constant was in the heat equation, although we can think about that more. But here, I do want to be careful about how I call the constant for the wave equation. Let me just do right now a very suggestive calculation based on units. Okay, so uxx, that's the derivative of the transverse position. That'd be like centimeters, with respect to two space variables, so that's over centimeters squared. And then this is some mystery unit squared, equals, now this is that same transverse centimeters, but with respect to time twice. And so these guys are matching, because they both come from u, so let's just cancel those out. And so I need something here that turns 1 over centimeter squared into 1 over second squared. So that's going to be centimeter per second all over squared. So c has units of centimeters per second, and that's the units of a velocity. And it turns out that c is a velocity. It turns out to be the velocity of wave propagation in this medium, whatever this string is. And it depends on things like the density and the tension in the string, if we want to do the physics of it. But that's all I wanted to introduce you to right now.